A few little things to clean up here before we move on to chapter 2. Again, don't copy this down. It's in your book. So it's the properties of infinite limits, and what we have is two functions like we've had before, f of x and g of x. One of the functions has an infinite limit as x approaches c, and the other function has a finite limit, L. And so just like before, we have these rules for adding functions, multiplying functions, dividing functions. And I haven't figured this one. I looked at this one. We'll get to that. I think this is wrong, but anyway, so if you have two functions and one of them has an infinite limit at x equals c, by adding the two functions together, you don't get rid of that infinite limit. And it makes sense. I mean, if you have vertical asymptote, you really can't get rid of that vertical asymptote. It's stuck, it's there. Likewise, if you have a function that has an infinite limit, you might say, well, I could multiply it by 0 and I might get something, but in reality, that actually doesn't happen. So this theorem here, these theorems on limits or properties on limits basically say if you have an infinite limit and you try to get rid of it by multiplying or adding another function that does have a finite limit, you can't get rid of that infinite limit. Now this is the one I don't understand, because this is infinity and this is a number. So infinity over a number should be infinity. So I don't know why it says 0. So I don't agree with that. So I have to check that out. There's really no place that we actually use this that I know of, but it's it's in the book, so we're going to cover it. Okay. The next thing is the flow chart I gave to you. So go ahead and pull out the flow chart, and I've actually got some links here. So we have the two sides of our handout, and I've got a few extras if somebody didn't get one. As I said, you can bring that into the test. So what we're looking for, the one is it says flowchart for evaluation of limits. So the basic process is, first you always plug the number in there and you see what you get. If you get a number, then you're done. If you get an indeterminate result, then there are 4 options. 3 of the options here, if you have a ratio of polynomials, you can use the dividing out technique. If you have a square root, you can use rationalization. And if you have trig functions, you can use the squeeze theorem to remove the indeterminacy and determine the limit. The other indeterminate example is the absolute value over the same term without the absolute value. In this case, you can't remove the indeterminacy, so the limit just does not exist in this case. And the limit does not exist at x equals c, but everywhere else the limit does exist. And these, the limit does not exist at one value where the expression is indeterminate, but probably all the other values of x, it probably is it's just the value of the function. And then the final one is, if you get plus or minus infinity, the limit does not exist. So that's at vertical asymptotes, usually, those kinds of things. Okay, so those are the options. So you can kind of follow your way through when you do the test if you need that extra help. As far as one-sided limits, it's the back of the paper. And it looks pretty much the same. So you still, if you're taking the limit of f of x as x approaches c from either the positive or the negative side, the left, right, or the left-hand side, the first thing you do is you plug in the value of c into the function, and if you get a value, if you get something other than indeterminacy or infinity, that's your answer. So always plug the number in. There's going to be at least a couple of problems on the test where all you do is plug the number into the function. Another thing to remember, and I'm thinking about it, remember the trig function, the squeeze theorem only applies as x approaches 0. So if you see a limit where there's a trig function involved, it's indeterminate, and you don't see the limit going to 0, then just just evaluate the function. Okay, back to one-sided limits. So first you plug the number in. So one choice is you get an answer. There you're done. If you get an indeterminate result, then you just use the same as you would for the just the two-sided limits. The only difference is if you get infinity. If you divide a number by 0, then use the techniques discussed in 1.5, which just means that you plug in numbers that are close to the value x equals c and see whether it goes to plus or minus infinity. So the handout that we did. So use the techniques that we used in the handout to figure out whether it goes to positive or negative infinity. So that's pretty much it as far as limits. Not super complicated. And then the last thing we're going to do here is we're just going to look at some of these piecewise functions that they have as exercises for this section. So this is problem number 20, and we're just going to go through and think about these. So we have the question of what is the value of the function, what is the limit. So those are the questions we have. So in this case, we have a piecewise function that has a vertical asymptote here at x equals -2. Here it jumps from, this is a hole, so, and then you have a dot. So the value of the function here is the dot, not the hole. And then you have a straight line that goes to this hole, so the function does not exist at this point. And then we have another vertical asymptote with a double root here, so that we have them both going to positive infinity. We do have a dot, so the actual function does exist at x equals 4, but on either side of it, the function is going to positive infinity. So that's what it is. We could come up with, it's probably these two are probably rational functions. This is a linear function. This is probably another another rational function with a double root in the denominator, and then we matched up the value of the function, this linear function, with the value of this function, so they meet exactly at the same point. Okay, so I'm just going to go around the room here. I'm going to start actually, so you don't always feel like you're picked on. Xavier, I'm going to mess it up. Xavier.
It doesn't really matter.
Sorry.
It's okay.
Okay, whatever it is. Okay. So what is the value of function -2?
Undefined.
Yeah. Undefined, does not exist, something like that. So that's good. Okay, Seth. So what is the limit as the function approaches -2?
It does not exist.
Yes, correct. It's because it goes to infinity on both sides. This goes to negative infinity, this goes to positive infinity. Okay, Evan. What's the value of the function at x equals 0? 4. Yeah, so it's not equal to a half, it's equal to 4 because the dot's there. Okay, Mark, what is the limit as x approaches 0 of f of x? Yeah, does not exist. It's kind of like a stepwise, like an absolute value, because as you approach x equals 0 from this direction, the limit is, so they don't have one-sided limits, but if I did a one-sided limit here, as x approaches 0 from the negative side, the limit would be a half, and if I took the limit as x approaches 0 from the right-hand side, it would be 4, and they're not the same. So since those one-sided limits are not the same, then the limit does not exist. Okay, let's see who we have. Margaret, what's the value of the function at x equals 2? Yeah, it does not exist because it has a hole. Okay, Michaela, what's the limit of the function as x approaches 2? Well, let me ask you this question. So here's 2, and this function is approaching some value of y, which is what value y? if I go over here horizontally, this is 1, so that's probably half, yeah. And if you come from the right-hand side, this part of the function is still approaching a half. So in this case, the function does not exist, but the limit does exist, okay? Maya, what's the value of the function at 4? 2, yes. So even though we have vertical asymptote, because there's a dot here, the function equals where the dot is. Now, this function is not continuous at this point because you have to raise your pencil to go from here down to here, you know, from infinity to down to here. So it is not continuous, but the function exists there. Okay. Kreia, what's the limit at x equals 4? Almost. So because it's technically when we just have a limit, which is not a one-sided limit, just a limit in itself, even though it is going to positive infinity, we would say that does not exist, okay? Now, if I asked you what is the left-hand limit, you could say positive infinity. If you said the right-hand limit's positive infinity, then you might say, well, they're the same thing, but infinity does not exist, so you can't, so we would make that, we would say the limit does not exist. You know, over here, it's not so confusing when it goes from negative infinity to positive infinity, that they're not the same thing. So you wouldn't say that goes to positive negative infinity. So the same things, even though they are going in the same direction. So that's why I'm doing these, because there's these little subtle little things. You won't have to worry about this for the test. This is just try to understand some of the little subtle things. And then we got problem 22. So let's continue here. Who's next? Kelly. What's the question here? I've got a problem. What does it say? Use the graph to identify the values of C for which the limit exists. Okay. So let's break it up into a couple of parts here. So the first part is going to be from here to there. Then we're going to ask the question at -4, and then between -4 and not all the way to -2, but just before -2, okay, and then at 2. So that's the kind of question. So I'll tell you what I'm asking, and then you can. So does the limit exist for this function between x equals negative infinity and just to the left of -4? It's a yes or no question. Yes. That's correct, okay, because this is a continuous function and there's no vertical asymptotes, there's no holes, okay. So Jacob, does the limit exist at x equals -4? Yeah, you're trying to think, is he asking me, does the function exist or does the limit exist, or what, you know, yeah. So, and yes is correct, okay. You have 50% chance on this one. So the limit does exist because as we approach x equals -4 from the left-hand side, we're approaching 2, y equals 2, and as we approach from the right-hand side, we are approaching 2. So the limit does exist, even though, and the function does exist as well. It's not, the function exists, but it's not equal to the limit. So because of that, you know, we don't have continuity here. If this dot were moved up here, then it would be continuous. Because the dot's down here, it doesn't satisfy all 3 requirements. The function exists, the limit exists, but the function value does not equal the limit. That's the one that fails. Okay. So between -4 but not equal to -4 and -2 but not equal to -2. Who's next? Christian. Does the limit exist between x equals just to the right of -4 and just to the left of -2?
I want to say no.
Why do you want to say no?
Well, I'm kind of confused me because I know it doesn't exist at like -2.
Yeah, it doesn't exist at -2, but does it exist just to the left of -2? And the answer, I guess, that's kind of like is the universe finite or infinite? It's um, how many people will think of it? No, just I'm kidding. But I would say it is continuous because it approaches infinity, negative infinity, but never equals negative infinity. So I would say it probably does exist. Now at x equals -2, and Daniel, I was thinking H, but that's your last name, Daniel. Does the limit exist at -2? Okay. Yeah, the function exists, but the limit does not exist because as you approach x equals -2, this goes to negative infinity, this goes to negative infinity, it approaches negative infinity, but it never equals negative infinity. So that the limit does not exist. I'm just going to skip to this one. So yes, Tessa. Does the limit exist at 0? No. Yeah, she's reading my eyes here. Yeah, the limit does not exist. Does the left-hand limit exist? Yeah, and it's equal to 0. And the right-hand limit is equal to 5. And because those are different, then the limit does not exist at that point. It's not continuous. So why is it not continuous? The function exists. The limit does not exist, and the limit does not equal, only the right-hand limit equals the function. So this fails two conditions for continuity. And let's see, Zane, does the limit exist at x equals 3? Yes. And it equals -3, yeah. So what's special about this particular point? The function exists here, the limit exists, and the limit equals the function, so it is continuous. What we'll find out, the special thing about this is that the derivative is undefined at that point. Because if you think about the slope of the tangent line here, it's negative, and this is the slope of the tangent line here is positive, but right here at the tip, it's undefined. It's like you could try to balance if I had a perfect knife edge, which of course isn't, it doesn't have, you can't balance any. Is the slope here or the slope, really don't know if it was a perfect knife edge. So that's why they put that in there, because later on we'll say the derivative does not exist there, but the limit exists, the function exists. Okay, and I've already assigned the homework, right? I guess today section 2 is due. So you don't have to hand it in now, just stick it on the corner when you leave. Crossing my fingers that you'll get your computers today. Oh, Christian, did you bring in that jump drive? Oh, you switched it? Okay. Okay, so we're going to move on to chapter 2 now. Just in case you don't get your computers, I'm going to find a way of letting you know how to access the test review this weekend if you'd like to look at it this weekend. Most people that'll be too early, but you can actually, let me just show you how to do this. Let me sit down for a second. If you go to a browser and go to YouTube, even if you forget, just seeing what the new videos were here. I saw a pretty interesting TV program about Voyager. That's the space probes that went to Jupiter and Saturn. That was pretty cool. It's on PBS. It's been 40 years since I guess they launched Voyager. Okay, but if you put in my name, my formal name here, Stephen Nicholson loves themes. Okay, that's not it. Put in calculus. You'll see that there's my calculus channel. It's not a whole lot in there right now. So I've been recording the classes, and I have this from spring semester, but I'll create one for fall semester. If you miss class, you can go to here and you can watch the class videos. So far, how many classes have we had? 6 classes. But I'll put a review up there. So that's all you have to do. Okay, so the first section in chapter 2 is called the derivative and the tangent line problem. The derivative is basically the value of the slope of a line that's tangent to the curve. So the way I'm going to do this is I'm going to derive it. Don't try to, just pay attention, okay? I'm not going to ask you to derive it. So what we want to do is we want to come up with a way of coming up with what is the slope of the tangent line to a curve at some arbitrary value of x. So in your homework for section 1, problem number 8, you looked at approximating the slope of the tangent line at a specific value of x by taking that x and y coordinate and then moving slightly one way to the right, this way, and finding the point on the curve and then drawing a straight line between those two and finding the slope using the slope formula. What we're going to do here is basically the same thing, but we're going to make it a general derivation for any function at any point. So we start, this is a parabola just because it's not linear, so it's more complicated than a line, but not quite. So what we're going to do is we're going to define a point, an arbitrary point on that line, and that point is going to have an x coordinate equal to x and a y coordinate, which is the value of the function at that value of x, okay? And then what you do is you then pick another point that is slightly to the right of that point of interest. What I'm trying to find is what is the slope of the tangent line at this point. So the point is defined, the location of the point is defined as being the x coordinate is not x, but x plus a small increment in x, delta x, which you can think of, if you want to think of it right now as maybe like 0.1 units or half a unit. So it's close to the original value of x, but not, it doesn't have to be like 0.00001. Right now, just think of it as far enough away that it's easy to calculate, but it's doesn't have an infinite number of decimals. So let's say this were 2. If we were talking about a specific case, this might be x equals 2, and this might be 2.1 or something like that. Just to give you an idea of what delta x may be to start with. And to find the value of the function at this value of x plus delta x, you just go up to the curve and then go to the right and to the left, and you have the value of the function at this new value of x. So it's f, the value of the function evaluated at x plus delta x. So again, if I just specific example, if x were 2, I'd find the value of the function at 2, and then I'd find the value of the function at 2.1. And that would give me the coordinates of these 2 points. But we're doing it in general. And then you draw a line between those 2 points, just like you did on problem number 8. And so we have a straight line. And this blue line, if I extend it, is pretty close to the slope of the tangent line. It's going to be a little bit steeper in this case. The actual tangent line is probably going to be just to the slightly smaller. And then you use the definition of the slope, which is the change in the y coordinate divided by the change in x coordinate. In our particular example, the change in the y coordinate is the value of the function at x plus delta x minus the value of the function at x. the change in the x coordinate is just this delta x. So the slope of that tangent line is that. Okay. So what we do in calculus, though, is we take the limit of this expression as delta x goes to 0. In your homework, when you picked your second point closer in terms of the x value, closer to the original x value, your line that you calculated, the slope of the line, was closer to the actual tangent line. So what we're going to do here, though, is we're going to take the limit as this delta x goes to 0 to get the exact slope of the tangent line. So there you go. And it turns out the slope of the tangent line, which I've defined as the limit as delta x goes to 0 of the value of the function at x plus delta x minus the value of the function at x divided by delta x, which is just the definition of the slope, is also what we call the derivative. So the slope of the tangent line is the derivative. And that's it. Okay, that wasn't very complicated, was it? But we needed to know about limits. And also, you know, if I let delta x equal 0, then you'll get 0 in the denominator, and you'll get the same value of the function in the numerator, so you end up with an indeterminate result. So we have to use those techniques we learned in chapter 1 to be able to evaluate that limit because it's indeterminate. So we're just going to do an example here, and I can't remember what's on my next screen, but I'm going to do it here. So basically what we're going to do is I'm going to do a couple of examples, and then you're going to do a couple of examples. And then we're going to look at these examples and kind of make some use reasoning to figure out, is there a formula that tells us how to go from a function to its derivative? Okay, so let's say the function is x squared, which is what actually we were looking at just a second ago. So what we need to evaluate the derivative is we need f of x, which we have. Then you have to evaluate the function at x plus delta x. So when you change the argument, all you do is, instead of having x in the original equation, we're going to put x plus delta x. So I always have put a parenthesis because that's clearly shows that I'm going to square the entire quantity. So that's f of x, whatever your function is. That's one I decided to look at. And to evaluate f of x plus delta x, you plug in x plus delta x in for x. It's kind of like a composite function. Okay, then you substitute in the definition, into the definition, which is just on the right-hand side, or left-hand side. I can't tell my left from right here. So, so what we say is the derivative in this case is equal to the limit as delta x goes to 0, approaches 0 of f of x plus delta x. So I use what I've come up with here. So I have x plus delta x squared. So that is f of x plus delta x. And then I subtract f of x, which is the function that I'm trying to find the derivative. So that's f of x. And then I divide by delta x. And again, if I set delta x equal to 0, I'll find it, this will go to 0. I get x squared minus x squared, which is 0, divided by delta x, which is 0. It's indeterminate. So in these problems, you multiply out f of x plus delta x, especially with polynomials. So we're going to take the limit as delta x goes to 0 of, so what is x plus delta x squared? We'll do that down here. Use FOIL. So it's the same, x plus delta x squared is x plus delta x times x plus delta x. So you multiply the first terms together and you get x squared. You do I is next, so you get x times delta x. This is not 3 terms, it's x times delta x. So there's 2 terms. We could put a little dot in there to. Then you do the outer, which is going to be x times delta x. And then you do the last, which is, and I'm going to put this in a parenthesis, delta x quantity squared. So when you simplify it, you'll get x squared plus 2x times delta x plus delta x squared. Okay. So now I'm going to plug that in up here. So once you multiply that out, the first term becomes x squared plus 2x times delta x plus the quantity delta x quantity squared. And then we subtract f of x, which is x squared. So what we're using here is we're going to use the canceling out technique. It's not exactly like we saw before, but it is some ways. So what we do is we cancel out that term with that term. So the x squareds cancel out. So cancel out x squareds. So what do we have left if we do that? We take the limit as delta x goes to 0 of 2x times delta x plus delta x squared. Well, we actually haven't canceled. That's not really, sorry, that's yeah, that was bad. Let's say what we're doing here is really simplifying. I got ahead of myself. Simplifying. So we're simplifying. We are canceling these out, but we're not canceling numerator and the denominator. So we're actually simplifying at this point. Okay, now we're going to cancel out. What we're going to do is we're going to cancel out the x squareds. So I'll write that out. Cancel out delta x in numerator and denominator. Or divide out, I guess. Maybe that's the way I'm supposed to say it. Divide out. So then once you've divided out the delta x, what you have left is 2x plus delta x. So this delta x cancels out with that delta x, and the delta x here has to also be dealt with in this second term. So you have delta x squared divided by delta x, which is delta x. Now at that point, the result is not indeterminate anymore. So we could say we are no longer indeterminate, meaning that if I plug in if I let, in this case, let delta x equals 0, here we couldn't let delta x equal 0 because you would get an indeterminate result, but by canceling out the delta x in the numerator and the denominator, we ended up with this simplified expression, just like we had before. So we, instead of, just like we did here, if it's indeterminate, if it's not indeterminate, then just plug the number in. So what you end up with is 2x, because this goes to 0 or equals 0. This one doesn't have delta x at all. So this is kind of like the limit of a constant. Limit of 3 as x goes to anything is 3. So this term remains, this term goes to 0. So what we can say is the derivative of x squared equals, I'll put that in parentheses, is 2x. Or we can say that the slope of the tangent line to the function f of x equals x squared is 2x. So at x equals 1, the slope of the tangent line is 2 times 1, which is 2. The slope of the tangent line at x equals 2 is 2 times 2, which is 4. So that's how it works. Okay, so I did x squared. Just a little bit of terminology. This is more to do with functions. If you have an x value and then you have this little black box, which is the function operator, if you plug in x into this function operator, what pops out is the value of the function, which we usually call y. So in the past, if we're talking about a function, we usually say if the function is f of x, sometimes we say it's y, because that's the coordinate we plot. When it comes to derivatives, when we take the derivative of a function, or to show that we've taken the derivative, we take f of x and we put a prime right here. So that's not a 1. It's like a little, what do you call that thing? A single quotation mark. If I were printing it, if I took my text here and I wanted to do it, I would say f, and then I would put a single, like that. Okay, so it's not a 1, it's a little prime. And that's read actually f prime of x. This is f of x. This is f prime of x. When you hear the prime, that means, oh, that's the derivative of the function. That's the slope of the tangent line to that function. Likewise, sometimes instead we might use the y designation for the value of the function. In that case, we'd say the derivative is y prime. So the prime is used to indicate the derivative. Before I didn't, so if I go back to my previous example that I just did, I used the word the derivative, but I could now that I've introduced the terminology, what I would say is instead of the derivative, I would say f prime of x equals the limit . There's also some other interesting ways that we'll deal with later. So you can also show the derivative by using these small d's. So instead of y prime, sometimes we use dy dx. And what we're really doing is we're saying d over dx. This means the derivative with respect to x of y. The derivative, or you could say the derivative of y with respect to x. It's also would be read as dy dx. Okay, even though it's dy over dx, you would say dy dx. Okay, for right now, we're just going to say it's the derivative is f prime of x. And when later on when you see these, I'll talk about it again. There's also, if you get into higher level math, they have this d, capital D, which is a derivative operator. This tells you what variable you're taking the derivative with respect to. But don't worry about those right now. Okay. So here's the formal definition, the one that we'll use from now on. So instead of saying the derivative equals, we'll say f prime of x. Okay. The prime again means take the derivative. So the definition of derivative is the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. So let's do another example for today. We should be able to do it in 15 minutes. So this is f of x. We need to evaluate the function at x plus delta x. So I'm going to write that out. F of x plus delta x equals, instead of x cubed, I have x plus delta x cubed. So now I have to use FOIL twice, or however you get, when you multiply out this. So here's a little question for you. This might be an Algebra 2 question. If you have a binomial like this, and you multiply this out, which is, a plus b times a plus b times a plus b. Does anybody know what the answer is here? I'll give you the first one, a cubed. Okay. Well, if it was negative here, yeah, you'd negative, but positive, it's going to be positive. So it's positive. Well, you're going to have one term that's going to be a squared b. You'll have another term that is, and then you'll have plus another term that's a times b squared, and then you'll have a third term which is b cubed. Kind of like, if you have a times b squared, you have a squared plus 2ab plus b squared. We just did that with the x plus delta x. So the question is, what are these coefficients? Anybody remember that? So I'm trying to lead you here. Okay. When you have a plus b quantity squared, the answer is a squared plus 2ab plus b squared. So that's, the exponent is 2, this is 2. The exponent is 3, so the coefficient is 3. Okay. It turns out if you have a plus b to the 4th power, it's a to the 4th plus 4 a cubed b plus 6 a squared b squared plus 4 a b cubed plus b to the 4th. So this coefficient is always equal to the exponent, the second and the next to last. The middle one's a little more complicated. Okay, I'm just saving, we could multiply it out and do it the long way, but I'm going to use my knowledge here of what it should be. So all we're doing is using FOIL. And so the answer is x cubed plus 3 times x squared times delta x plus 3 times x times delta x quantity squared plus delta x quantity cubed. So that's what you would get if you multiply out x plus delta x cubed. So all we have to do is now plug that into our limit, our formal definition of the limit. Of the derivative. So what we say is that the derivative of the function x cubed is equal to the limit as delta x goes to 0 of f of x plus delta x, which is this big long thing, x cubed plus 3 x squared times delta x plus 3 times x times delta x squared plus delta x cubed. So that's f of x plus delta x. And then we subtract f of x, which is x cubed. And we divide that whole thing by delta x. Now again, if I set delta x equal to 0, it's going to be indeterminate because everything's going to fall out. These are all going to go to 0, and these are equal to each other, so the whole thing goes to 0. And obviously, if you set delta x equal to 0, so the first thing we do is we simplify, and usually the thing you can simplify is that this cancels out with that. The first term of f of x plus delta x cancels out with f of x. So once we do that, let's write what that is. So we got the limit as delta x goes to 0 of 3x squared times delta x plus 3x times delta x squared plus delta x cubed, all divided by delta x. Then we divide out delta x, because you can see every term in the numerator has delta x. We have one delta x, we have delta x squared, we have delta x cubed. So once you've divided out the delta x in the denominator, then what you're left with is 3x squared plus 3x times 1 delta x. Let's cancel that with the squared. And the last term, delta x cubed, becomes delta x squared. And there's no denominator anymore. So we could say now not indeterminate. We've removed the indeterminate. We've removed the indeterminacy in the equation. So now we can just set delta x equal to 0 to evaluate the limit. So when we do that, the first term doesn't involve delta x. So this term remains unchanged. This one, you have 3x times 0, and then the last term is just 0 squared. So if you simplify it, all you're left with is 3x squared. So what we can say is that the derivative of x cubed is 3x squared. So that's kind of how it works, okay? We've done two. The simplest one is just x, the function f of x equals x. So what I'm going to do is I'm just going to go ahead and hand them out here. We're not going to start working on it till tomorrow. But the actual first problem actually just worked. Was x squared. I realized that after I did it. The reason I didn't choose just f of x equals x to start with, because it just seemed too simple, and I didn't want you to. So I'll ask you to do the first problem, see how good a note you took on calculating the derivative of x squared. So actually, why don't we do that? We've got a couple of minutes left. So look back in your notes and do the first problem. Just write it on the paper so you can think about it. Hopefully you took reasonably good notes there. What I'll do is I'll go back one page to show you how we did it for this more complicated case. If you didn't take notes, you can hopefully figure it out. So what you're going to do, what you did is the function is x squared. The value of f of x plus delta x is x plus delta x squared. And then they multiply it out. And then you go through the same techniques here to calculate. You simplify, you divide out the delta x, then you set delta x equal to 0 because you've removed the indeterminacy, and then you get the answer, which is 2x. Okay. If anybody gets stuck, let me know. Or you can look at your neighbor. They took better notes than you did. Oh, you're going on to the next one. Okay. You've already done that one. Okay. Don't do this one yet because you'll probably get stuck. I need to show you an example that's close to that. So I'll do that first thing tomorrow. What we'll do tomorrow is if you turn your paper over and you try to do if you want to go ahead and try to do something beyond the first problem, go to the third problem, which is actually easier. It's just 3x plus 2. Okay, that one you probably can do. The one that's 1 over delta x squared, that one is going to be, you probably need a little more background if you want to keep yourself busy. I guess the question is, did you guys put enough detail in your initial one?
Yeah.
Okay, so you multiplied that out, divided it out, so you did a lot of stuff in multiple steps in one thing, but that's fine. Yeah, so the ones that we're going to look at to help you do the ones on the paper are 1 over x, then you'll do 1 over x squared, which you still will need some help with. We're going to do the square root of x, which will use rationalization to remove the indeterminacy, and then we'll use a squeeze theorem and some trig identities to do the sign. So. And my